Next up, we have Oleg, who will be presenting PTP at Meta. Oleg is a production engineer at Meta, formerly known as Facebook, and is coming to us today from Dublin, Ireland. It's Oleg's first time presenting at Nanog, and it's a pleasure to have him speaking with us today. Welcome.
Hi, everyone. Oh, you can hear me. That's fine. So nice to see surviving crowd here, smiling, still full of energy. That's nice. Right. So thank you for the introduction. So yes, again, my name is Oleg, and I'm production engineer at Meta. And just to give a couple of words of what production engineer is, it's basically a person who is responsible for maintaining the system, so operation-wise, development-wise, but also in case of outages or big events on the site, we are the first responders to the incident. So no surprise then when we design a new system or a new technology which is introduced, we focus on simplicity, which is the core value for us to make sure we can fix a broken thing in the middle of the night. So in any way, with this in mind, I'll tell about PTP at Meta, how it came to the existence, why do we need this, what is it used for, and yeah, we'll talk about a little bit about the design. So we will talk about why PTP, how we deployed it at scale, and why we were not happy with that at some point, so we switched to and developed SPTP, and then there is a bonus section which I'm sure you will be all interested in at the end, so make sure to stick to the end. So why PTP? So first of all, PTP is a precision time protocol, which ensures you have really good time synchronization between machines, between hosts on your fleet. So you may ask, yeah, there is NTP already, why don't you just use NTP? So NTP has its own limitations. It's a very old protocol, and it does not design very well for the modern era. So it does not support any hardware accelerations. So yeah, anyway, it's outdated, let's just say that. And to demonstrate why we need PTP, why we need better precision, I usually use this example. I mean, that's a very simplified example, but it's the easiest to comprehend, I guess. So imagine we have the user who is writing or making a transaction to the database through the backend. So usually you have like a replication over there, and your insert or your write will end up at several backend or several database replicas. And imagine you are immediately reading right after that, which is a very common use case. You can think of, you put a like on your page, and then immediately you want to see this like being there. So write once, read multiple times. So the problem here is that if your replication for some reason is not fast enough, you may end up in the situation where your read hits the replica, which doesn't have the data yet, and this ends up being like old data. Imagine you liking something, and then you're refreshing the page, and there is no like on the page, right? It's a simplified example again, but just goes to show. Yeah, so the worst which can happen is that you actually get old data, which is terrible for any kind of financial decisions or any kind of decisions if you have old data when you expect the new ones. But and there are several ways how to deal with that normally, how to combat this situation. It's quite often called quorum reads. It's basically when instead of reading it from replica 3, you are always reading it from all replicas, and then you say, okay, it seems like the most common new version is X, so I will be using that one. As you can imagine, it's pretty costly solution, but that's typically what people do actually to combat the situation. Now imagine you can do something, and you actually, when you issue a read to backend 2, the database, the replica 3 in this case, will tell you, hold on, I don't have this data yet, but I know it's there, it's coming, so just stick around for a few microseconds or milliseconds, and you will get your data. You can actually get this, you can implement this, if you trust your timestamps. Like imagine you have synchronized time, absolutely the same time on all of the machines involved. So what ends up happening is you can trust the timestamp. You know that you wrote your data at time X. So you expect time X to be during the read happens, or you block the read. So that's the simplest example. And yes, attentive listener can say, yeah, you can still use NTP for that or any other network synchronization time protocol. And we tried that. So this is what happens when you use NTP for those reads instead of PTP. Because NTP is a software-based protocol. It does not provide you any guarantees. So the window of uncertainty, as we call it, is very large. And to make sure that you have really high probability of hitting your timestamp, you need to wait for a lot longer for this replica for the data to appear. So on the left, you can see the reads enhanced by PTP or precision, which are less than a few milliseconds in the microseconds range. And on the right, you can see the NTP powered linearizability or external consistency powered by NTP. So you can see there is a lot higher latency, a lot slower reads, and generally not good. So there are other use cases why PTP is actually good it's used. Those are actually real life examples which we're already using. So read consistency, hybrid logical clocks at scale, latency measurements, and all sorts of actually measurements, and congestion control, which I'm sure you all are interested in, event tracing, and all sorts of monitoring. There are also some interesting use cases in AI space. Like, for example, if you have a bunch of GPUs, and it's always like a silicon lottery. You sometimes win, you get a better one, and sometimes you get the worst one. So you can actually categorize your GPU performance based on the nanosecond precision PTP gives you. But I'm just giving you some examples here. So let's talk about how we deployed PTP at scale at Facebook. So typically, this is like high-level architecture, and typically we split it into 3 parts. So it's a PTP rack, which has all on the antennas and all that stuff, and then the network, which I'm sure most people here will appreciate, and then the PTP client. This is the part where you actually give the time to the user and usage. So let's talk quickly about the PTP rack. So this is a typical PTP rack in the Facebook data center. Every rack has 4 time appliances. You can see them on the bottom, 1 Calnex monitoring device, optical antenna on the roof, and the transparent clock-enabled switch. This is very important. We will come back to this later. And we have 4 racks per region, like that, which means they use all different antennas, different power source, different monitoring, and they all have deterministic distance between them and the client, which is 6 hops. Again, we'll come back to this. This is very important. So the time appliance itself is just a typical server, but what makes it a time appliance is the thing called Facebook Time Cards, which we developed and fully open sourced a few years back. So this is a very cool thing which has the GPS receiver or GNSS receiver on board, which generally gives you precision of 12 nanoseconds. So this is as good as it gets in the modern era. And then we have atomic clock, which allows you to basically keep your time synchronized if in the event of the loss of the GNSS, like for example, there is jamming, spoofing, or just general outage. There are some outages happening in the GNSS, which may surprise you. And in general, those atomic clocks are designed to keep time within 1 microseconds for the 24 hours. But in reality, it's 1 microsecond per 4 days. So it's a lot more to keep within the SLA. So in our case, if we lose GPS or GNSS everywhere in the world, we will be fine for 7 days and not violating any SLAs which we promised to our customers. So then this is just a typical DL380 HPE server, which we plug the time card in, and it then can handle up to 1.5 million clients. But in reality, we just need 100,000 QPS. It's a normal operation. We just need to build for cases of degradation. So because we built our own time appliances, we need to make sure we properly monitor them. And we deployed a solution from Calnex, which is basically an independent assessment client, which pretends to be NTP client, PTP client, and also has the PPS. And we deploy them in the racks, and they cross-monitor each other and send data to our monitoring systems in case something's happening. All right, so let's talk about the network parts, the fun parts. So what makes PTP actually possible and why it's so drastically different from NTP is a thing called transparent clock. So transparent clock is the feature of ASIC of the network switch of the Broadcom or Cisco, for example, which timestamps the packets which are passing through the switch when we're traversing the switch. And it timestamps them to capture the residual time of the packet on the switch. So to give you a typical example, when packet passes through the ASIC of a modern Broadcom, let's say, switch, it takes approximately 700 nanoseconds to be processed within the switch ASIC. So what will happen is you will add this time into the packet and then right before shipping the packet further. So as you can imagine, 700 nanoseconds is not much, but the thing is, sometimes you have buffering, sometimes you have congestion, sometimes you have many things which are impacting this residual time. So, and I personally seen packets sitting on the ASIC of the switch for a few microseconds, so, or like 100 microseconds. So it's thousands and thousands of times of normal operation. So because of big buffers and things like that. So it's really important. NTP and other network time synchronization protocols don't have that, and we're really grateful for the network equipment manufacturers for supporting this feature. Right. In any case, so when packet passes through, it gets timestamped, and it gets timestamped on the client and on the time appliance itself. So, which means we all rely on hardware. This, you can think of this protocol as hardware enhanced, and because we trust the hardware, your math to calculate the clock offsets, the clock precisions are really simple. It's just formula on the bottom, which is really, really rudimental compared to NTP intersection algorithms. So here is a good example what happens when you don't have transparent clock enabled on just one switch in your network out of those 6, as you remember, as I mentioned. So you see the synchronization was pretty good. It was like -9 nanoseconds, 17 nanoseconds, so really in the nanoseconds range. And then suddenly it blew up out of the proportion. So it's like 200 microseconds now, 430. So you may go to the millisecond range if your transparent clock functionality is not enabled. So the moment we enable transparent clock on that faulty switch, you see we immediately got flat and got back into the range of nanoseconds or single or double digit nanoseconds. So it's extremely important to keep this functionality, to keep this timestamping on the hardware, and yeah, never break it, never diverge from it, because it only, most of the manufacturers only support timestamping of specific packet signatures. So it's a special PTP packets. So when we're talking about clients, we have to talk about PTP4L. So this is a very typical client which is used almost everywhere. PTP as a protocol coming with the legacy from the telecom industry. So as I said, it's relying heavily on the hardware timestamps. So you need to have the hardware timestamp filter supported by your network card. However, you can still use software timestamps, and here is a good example from one of the manufacturers of the NICs. When you see the synchronization was excellent, it's like 1 nanosecond, -5 nanoseconds, something along those lines, and then all of a sudden you get 200 microsecond spike, and then it's good again. So what happened here is basically the network card manufacturer could not produce a hardware timestamp because it's a pretty old NIC and it couldn't keep up with the traffic. And instead they said, okay, we'll just fall back to the software timestamps without telling us that. So we had to implement a filter mechanism inside, which would just basically forbid from having those spikes and will filter them out. But you couldn't do anything. It's just the hardware just cannot keep up with the traffic. So to make sure we are very reliable, we also implemented sharding. So every client is tracking more than one time appliance. It's tracking multiple time appliances at the same time. But how PTP protocol is designed, you don't really compare one performance-wise, one against another. You actually trust what time appliances tell you. If they tell you, I am good, my synchronization quality is excellent, and yada yada, client will just pick this by trusting it. And that's one of the fundamental disadvantages of PTP itself, because it was relying on multicast for existence. You basically don't have this feedback loop. You just trust the time appliance, what it tells you. So when the time is finally when you synchronize the client network card, when you synchronize the client, what clients really need is the time in their software. So we provide them with the FB Clock API. So this is the API library which is using similar concept as Google TrueTime, if you ever heard of that. So because the synchronization levels are so tight, you usually never tell just what you think of time as like time now. So you don't tell exact nanoseconds. Instead, you tell a so-called window of uncertainty when you say time is between X and Y. And this window of uncertainty allows you to put really high guarantees on everything, including PCI Express delays and other accumulated delays. So by accumulating all of that, you can actually provide high guarantees. As a matter of fact, we give our customers a guarantee that time is correct with 6 nines guarantee, at least 6 nines. So that's an example of the distribution. So what we provide them is this window of uncertainty, and you will get time earliest and latest somewhere between 200 nanoseconds. So this will be earliest versus latest of 200 nanoseconds difference. Right. So I mentioned already that we had to implement our own filter. I mentioned already that we have this disadvantage of blindly trusting the time appliance, and there were very many disadvantages to existing PTP client called PTP4L. And we decided at some point that enough is enough, and we decided to rewrite it. And instead of using the PTP4L, we decided to write our own client in Go, actually, which is a very popular topic through Nanoc this year, I can see. And we also, while rewriting it, we also decided to improve the protocol itself a little bit. So this is a typical two-step PTP exchange. As you can see, it's actually 11 steps for the negotiation and exchange of the timestamps. And you can see it's really excessive, like it's bloated even. You have 11 exchanges, but in reality you need only the timestamps, T1, T2, T3, T4, and 2 correction fields, which are populated by the network equipment. So that's all you really need, but it's a lot of complexity because it's telecom past. So in the telecom you use, at least quite often, you use multicast. You have really strict capacity limits, and you have top-down architecture. Your time appliances will go and tell you, you are getting time synchronized this often or that often. So it's really top-down approach in the telecom. And unfortunately, we had to adopt this at some point. But yeah, as I mentioned at the beginning, we had enough of that, so we decided to rewrite it. So we threw away everything else what is not really essential for the time synchronization, and this is the exchange we got. So instead of 11 steps, we now have only 3, which basically, but because it's hardware enhanced, and we use same timestamps and correction field and everything from PTP as before, it's exactly the same formula we use, so nothing changed here. So if we break it down, it's basically a client sending the packet, recording the timestamps, correction field, and then we populate all of those. This is the entire exchange. Like using this, you can implement yourself the SPTP exchange. For the PTP with 11 exchange steps, it would be a couple of slides worth of text. So looking at the TCP dump here, for example, when we send a delay request with SPTP, we specify the flag, which allows it to distinguish between old PTP v2 versus the SPTP. And you can see the TCP dump even still recognizes it as PTP. We really didn't want to change or break this compatibility because of all the hardware support of the timestamping and transparent clock. So we just shuffle packets a little bit and put the information in the packets slightly different, and then we pass those packets down to the client. What's very good here is that apart from the timestamp and the correction field functionality, we also have a typical unknowns message information. Like for example, you can see here at the bottom, we have the UTC offset. We have the time source, which means it's connected to GNSS. We have clock accuracy, clock class, and all that stuff is embedded into the packet. So it's all getting to the client together with the synchronization information. So because we were also worried that rewriting hardcore C application, PTP4L, into Go would come with the penalties, we were actually thinking, okay, so we should slowly roll it out and see if there is any impact on the time synchronization performance. And turned out there isn't, because it's all relying on hardware. And yeah, we tested it to hundreds of thousands of the machines. Now it's running on few million machines, and the synchronization quality is exactly the same as before. It's just a lot less power resource consumption. So for example, it's 40% less CPU consumption, 70% less memory consumption, 50% less network utilization improvement. So things like that are coming basically for free when you use SPTP. But one of the most important things for me as a production engineer, personally, is that we significantly improved strong reliability and fault tolerance. So, for example, if in the past we were just blindly trusting the time appliance telling us, "I'm good, use me," here now we can actually now issue all the requests to all the time appliances at the same time and compare the results in parallel at the same time. Because we are also running a fabric network, forward and reverse path can be completely different, and it's very important to make sure those measurements are happening at the same time as close as possible. So as a result, we get the client-driven exchange, no negotiation, no state in the memory, low resource consumption, and simple implementation. And I cannot overstate this. PTP4L was 10,000 lines of hardcore C versus under 1,000 lines of Go code. And as a matter of fact, many manufacturers already implemented SPTP on their devices. It's already working. And we use existing hardware enhancements and hardware timestamps. As the disadvantages is we don't have this negotiation anymore, so we have less flow control and no multicast support for the PTP, which was never the case anyways. So it's not a big for us. In any case, everything is open sourced. You can find it on GitHub. Everything I spoke earlier about, including the time card, the hardware, the software, SPTP, everything is on GitHub. For SPTP in particular, you can just go to SPTP info as a shortcut to get you to our GitHub libraries. So the last thing I wanted to talk about is a bonus section. So you know how when you implement something and then you can find different use cases for that. That's how you know it's actually an interesting thing that you can scale up and apply to many things. So this is the case with SPTP. So you all know the standard ping CLI, which you can measure latency between two random hosts. So you ping host 2 from host 1. And it usually shows you the latency, and we're all used to this output, but there is something wrong with this output, right? First packet shows you 84 microseconds, and the last one shows 174. How is it possible? Why do you have such a big latency difference between, just pinging between two hosts? As a matter of fact, because ping is not just measuring the network latency, it's actually measuring the network stack of the host itself. And this actually creates a problem because on a busy machine, on a busy host, on a busy kernel, you may have really high spikes just because of that. And you're not really measuring the latency between the network cards themselves. Now imagine those two hosts are synchronized with SPTP or PTP or whatever, and they are synchronized to the same source. So now you can actually trust the timestamps and you can do one or two-way latency measurements. And here the SPTP exchange, which we described earlier, is really handy because it's exactly what you can do. You can actually exchange those packets, get the timestamps, which are hardware timestamps, which are super precise because they're synchronized to the common clock reference. So that's exactly what we did. And this is how the same hosts, how the output looks on the same hosts compared to the ping. So instead of 84 microseconds or 174 microseconds, the real latency between the machines is actually 38 microseconds. It's just the rest was eaten by the network stack and everything else on the way. But what's more, you can actually see that a forward path took 23 microseconds and a return path took 14 microseconds. So it could be possible only if, in two cases. First is hosts are not really synchronized. So you have one host drifting, another one does not drift. Or second possibility is that you have large asymmetry in your network. And knowing the speed of light in the fiber, you actually can estimate the asymmetry is around 2 kilometers of the fiber of forward and return path. And because we use these announce messages, you remember where the time appliance tells you, I'm good, I'm synchronized, I'm in a good shape. because they baked into the SPTP protocol, you can actually get the information about the synchronization. So you know that both hosts are actually synchronized and they are both working very well. So it's in fact an asymmetry which we detected using our ping, which we call PT ping, play words. Anyways, yeah, so that's pretty much all I have today. And yeah, thank you.
Are there any questions? Anyone? Bueller? All right. Thank you, Oleg. That was a great talk.
Thank you.